Now that we've finished discussing how nature works, let's talk a little bit about nurture. When DNA is condensed, it's wound around a protein known as a histone. The more tightly wound a DNA is to a histone, the less likely the DNA is going to be able to be unwound and therefore accessible for transcription. You remember how we talked about that whole cyclin CDK complex activates the retinoblastoma protein and deactivation of the retinoblastoma protein allows for DNA synthesis to occur? We've got another protein regulation going on, but this time it's with histones. Because histones are proteins as well, they're also made up of a bunch of amino acids bound together. One of those amino acids, lysine, is a basic amino acid, which means that it has the potential to become positively charged. When the acetyl group is bound to lysine, it prevents lysine from being able to bind directly to DNA. Which will change the charge not only of lysine, but of the entire protein together. When you add an acetyl group or acetylate the lysine amino acid within a histone, you make that histone no longer able to bind to the DNA, which allows that DNA to be more accessible for transcription. When you remove the acetyl group from a histone, that histone can bind to the DNA. So when there is an acetyl group on the histone, it's not able to bind to the DNA. When the acetyl group is removed, the histone is able to bind. One thing that the environment does is changes how often an acetyl group is added to lysine. If more acetyl groups are added to lysine, you're going to have more accessibility for the DNA and more transcription. Increased acetylation of lysine, increased transcription. Decreased acetylation, decreased transcription. How is an acetyl group removed from lysine? Histone deacetylase. If you increase the function of histone deacetylase, that means more histones are going to have their acetyl groups removed. The removal of the acetyl group allows the histone to bind to DNA, which means that the DNA is not able to be transcribed. So when you have increased activation of histone deacetylase, that's going to lead to a suppression of transcription. If you decrease the function of histone deacetylase, you're going to decrease the removal of the acetyl groups, which means less histones are going to bind to DNA. More transcription is able to occur. So reducing the function of histone deacetylase will lead to increased transcription. And the function of histone deacetylase can be increased or decreased by the environment. In addition to altering histones, the environment can also alter the DNA directly through something known as methylation or adding a methyl group. Similar to adding an acetyl group to lysine change the function of that protein, if you add a methyl group to cytosine, you're going to change the function of the DNA. When the cytosine is methylated, depending on where this methylation is occurring, it's either going to increase or suppress transcription. When people refer to epigenetics or the impact of the environment on genes, two of the mechanisms genes are impacted is through methylation of cytosine and through acetylation of lysine on histones. So back to the question, why is she developing symptoms now? Her body could have been making more proteins to keep up with whatever decreases she's experiencing, so the symptoms aren't there. She also could have been experiencing these symptoms her entire life. We also could just not know. Science is a consistent pursuit of God's mind, and we're never going to fully be there. So there's always going to be things that we just have to say we don't know because we're not there.